Welcome back. In example 2, we have the base of a solid. That's the region between x equals 0, that's the y-axis, x equals 2, that's this vertical line on the right side of figure 18, and then y equals 0, which is the x-axis, and y equals x plus 1, which is this line. It's kind of like a 45-degree line, but going through the y-intercept at 1. So it says cross-sections perpendicular to the x-axis are isosceles right triangles, with hypotenuse in the base. Now this is going to be one of the key words that's going to differentiate these kind of problems from the volumes of revolution, from the solids of revolution. Here, there's no axis of that we're revolving things about. We're just told what the cross-sections are. It says the cross-sections perpendicular to the x-axis are isosceles right triangles. So if we look at a cross-section, if we take our solid and slice it, like slicing a piece of bread, right? We're going to get an isosceles right triangle. A very strange looking piece of bread, but anyway. And anywhere you slice this solid, that's what the cross-section is going to look like, an isosceles right triangle. So if you were to imagine what this solid would look like, it would look something like figure 19. You'll get smaller isosceles right triangles on the left, and then bigger isosceles right triangles on the right. Now, another part of it is that it says the hypotenuse of the right triangles is in the base. So this angle up on the top of these triangles, as drawn in figure 18, is a right angle. And the hypotenuse, which is the opposite of the right angle, is going to be along the base. The base is talking about the bottom of this solid that we're making, which is basically the region in the xy plane. So the hypotenuse is going to be along the base, and then the right triangle, the isosceles right triangle, will come up out of the xy plane. And if it's an isosceles triangle, that means that this side here that's popping up out of the xy plane will be equal in length to this side that's popping out of the xy plane. Even though in the picture it's kind of at an angle, so it's a little hard to tell that these two are supposed to be the same length. But if it's an isosceles triangle, then this side here is going to be equal to this side, with the right angle in between. So in fact, this is going to be a 45, 45, 90 triangle, your good old friend from trigonometry. Let's take a moment and draw a picture of one of those cross sections. So we'll draw it like this. Those are the two equal length sides with the right angle in between. And then we've got the hypotenuse down below. So we're just taking this triangle and drawing it flat so we can start to analyze it and try to figure out what's going on. Now, one thing for sure is that this hypotenuse is along the base. It's inside of the region. So we're going to be able to figure out, given an x value, that cross-section is at, we're going to be able to figure out exactly how long that hypotenuse is. We'll get a formula for how long these hypotenuses are. And one of the things that'll help out is noting that this curve here is the y equals x plus 1 curve. So if we think about this distance from the x-axis up to that y equals x plus 1 curve, that distance is just going to be x plus 1, right? It depends on what x is. That distance depends on what x is. If x is here at x, then it's just x plus 1. If x is 0, it's going to be 1 for that distance. If x is 2, which is over here, it's going to be 3 for this distance. The hypotenuse will be 3. But in general, the formula is whatever x value you're at, the hypotenuse has a length of x plus 1. All right, so let's label that over here. This is x plus 1. But now if we want to find the area of this cross-section, the area of this isosceles right triangle, then we're going to need to know what these legs are. If you think about the formula for the area of any triangle, It's going to be 1/2 base times height. Now, we could take the hypotenuse to be the base, but then we'd have to figure out this height up here. But another way we can think about this is to plop one of these sides, one of these legs, down so that that's the base, and then the other leg here will be the height. If you imagine this sitting more in this orientation with the right angle right here. So we could take the base to be one of the legs, and then the other leg will be the height. So 1/2 base times height. Okay, I'm going to leave it over like it is here, and start labeling these with something, because we don't know exactly what these lengths are, so we're going to label this, let's say A. Now if that's A, the other leg is A as well, because it's an isosceles triangle. Those are the two equal sides. And now what we could do is try to figure out what A is. Well, what's an equation that can relate all of these sides together? So if you said the Pythagorean theorem, that would totally be correct. Not even a little correct. That's very, very good and correct. All right, so we have a leg squared plus a leg squared equals the hypotenuse squared. That's the Pythagorean theorem. Now let's solve this for A in terms of x. So we'll be able to get what those legs are as a function of x. So we have 2a squared equals x plus 1 squared. Divide by 2. And we get a equals x plus 1 over the square root of 2. Again, there's a little side note that we could write here about x plus 1 being positive, but we'll leave it at that. So a is x plus 1 divided by the square root of 2. By the way, if you knew that this was a 45, 45, 90 triangle, our standard 45, 45, 90 triangle, we could compare it to one that we often use in trigonometry with legs that have lengths 1, 1, and root 2. It's kind of like you take the unit square, you take like a unit square and you cut it in half, and by the Pythagorean theorem, the hypotenuse is root 2. So this is like a typical 45, 45, 90 triangle that you can use for all of your trig functions, like sine of 45 is 1 over root 2, and so on. But we can use it here to avoid a little bit of work with Pythagorean theorem and realize that if these two are 45, 45, 90 triangles, then they're similar triangles, and similar triangles have sides that are proportional. So we could think x plus 1 over the square root of 2 is equal to a over 1. So we could do x plus 1 over the square root of 2 is equal to a over 1 just by using proportional sides, right? But then we get immediately what our result was right here. We get a equals x plus 1 over 2. Another way you can think is to get from to get from the square root of 2 from this side over to the 1 this side, you'd have to divide by the square root of 2. So similarly, on the bigger triangle, to get from this side x plus 1 to this side, we would have to divide by 2. So x plus 1 divided by 2 will equal a. Another way to think about it. All right, but we've gone long enough on that tangent. So let's go ahead and write the area of this triangle now that we know what the legs are in terms of x. It's going to be 1/2 times the base, which we'll take to be one of the legs, times the height, which we'll take to be the other leg. And on the top, we're going to get x plus 1 times x plus 1. That's going to be x squared plus 2x plus 1 if we multiply everything out. After all, we're going to have to integrate, so it's nice to have it multiplied out. Then on the bottom, we've got 2 times the square root of 2 times the square root of 2. Well, the square root of 2's will become a 2, and then you have another 2, which will give you 4. So then now we've gotten past the hard part. The hard part is just trying to figure out what those areas of those cross sections are as a function of x. Now that we have that, we'll plop that area into our integral. And what are we integrating from and to? So if you said from x equals 0 to x equals 2, that would be correct. That's the left side and the right side of our region, of our solid. 0 to 2. So then we have the integral from 0 to 2 of 1/4 x squared plus 2x plus 1 dx. And from here, you integrate, find an antiderivative, plug in the limits of integration, and you should get 13/6. So I'll put a little dot 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 right there. Great. So that's it for example 2. In the next part, we'll look at example 3. Thanks for watching.